Yeah. All right. Thanks for coming. So today I want to talk about how to verify. Now, hopefully, all of you are really motivated to learn about post-quantum signatures on Ethereum, and this is a joint work with Ruslan, Peter, and Nandor. And so, what's the TLDR? Maybe you need to run or something. If you want to see our Solidity libraries that we developed, you can access them at this link. And also, you can see the paper on ePrint. If you want to read it, it was accepted to Asia CCS. So if you are in Asia CCS at the end of August, we can meet and talk about this paper again in Vietnam, Hanoi. So as you know, Ethereum need to transition to post-quantum crypto. And what we did in this work is that we benchmarked 3 hash-based signature schemes and 1 MQ signature scheme in Solidity. And we evaluated 2 verification modes. Don't worry, I will talk about it later. And yeah, we release everything that we do is we release it open source, so you can have a look at it at our Solidity libraries, and you can already use it on mainnet Ethereum if you want to verify and already transition yourself to post-quantum signatures. Yeah, so these are the TLDR gas cost numbers. So we looked into VOTS plus, XMSS, Swings plus. These are the hash-based signature schemes, and Mayo is the MQ signature schemes. These numbers were already cited by Antonio. So these are the gas costs, pretty high, but some of them are still better than Falcon. And these are the USD gas costs to verify a single signature on chain. And it's okay if you don't know what's an ACR verification mode. I'm going to describe it soon. Okay, so I just want to describe in the beginning some preliminaries, background on Naysayers proofs, our system model, and then I will describe at a very high level these 4 post-quantum secure signature schemes: VOTS plus, XMSS, Swings plus, which is already standardized by NIST, as you've already heard already today, Mayo, and I will close off with some, hopefully I can inspire you with some open problems and future directions. Okay, so you all know I just want to sacrifice one slide. I think it's just interesting to look at post-quantum cryptography and quantum computers as an analogy to nuclear energy. So even in the 1930s, there were high-profile scientists, like this guy's is a well-known physicist and chemist from, he was the dean of Imperial College London, and he was saying in 1939 that he thinks that there's a 1 in a million chance that people can build atomic bombs, and then we know what happened 6 years later in Hiroshima and Nagasaki. And if you ask ChatGPT and other experts will say that there's 1 to 5% chances that we can build quantum computers that are capable of breaking cryptography. So my point is that I wouldn't bet against technological advancements, so it's wise to be conservative and think about post-quantum transitioning. Okay, so let's jump into it. As Antonio already said 2 talks ago, there's lots of pre-quantum cryptography in Ethereum today, transaction signing, KZG commitments in EIP 4844. We have pre-compiles to compute pairings and group operations on the BN, BLS curves. Yeah, Zk rollups, we have hash functions. So generally, there's many cryptographic primitives that we need to reconsider once we have a quantum computer. And in this talk, I just want to focus on transaction signing. So this one. And so how users can sign if there's a quantum computer that's capable of breaking discrete logarithm and breaking ECDSA, then how can we sign transactions? Okay, how many of you heard account abstraction? Hands up. Okay, so everybody. So the point is that on chain, there will be smart contracts that can verify user signatures. So basically, if Alice or Bob comes from the street, they can define whatever signature scheme they want to use already on layer 1 Ethereum. And this is nice, and gives us a lot of modularity, but it's also a little bit risky, right? Because you can cook up your digital signature scheme in your kitchen, and if you want, you can use it on chain. Okay, so EOAs will have EVM code. And the point is that signatures will be verified on-chain by smart contracts. So this is kind of good for us because we can build custom Solidity libraries that enable us to verify post-quantum secure signature schemes, and this is exactly what we did in this work. Okay, so if you think about a digital signature scheme, it consists of 3 algorithms. And from a blockchain deployment perspective, the only interesting thing to us is the verification, because key generation and signing happens off-chain, so it doesn't cost us any money, right? And we only care about money. Just kidding. So what we really care about in this work is verification, because that burns gas and that costs money to our users. And what's also interesting is that signatures are not stored permanently in the storage. So typically it's in call data or blob data or something. So the point is that it's kind of entirely different design space as TLS. Because if you think about how there was a lot of discussion in the post-quantum crypto community, how we could transition to, how we can transition TLS into post-quantum secure TLS. And in that case, you both care about the size of the signature and the size of the public keys, because the certificate chains contain both of them, right? But in Ethereum, we don't really care about, we are fine with largish signatures. We only care about public keys because public keys must be read from the permanent storage, while signatures are in cold data or not in permanent storage. Okay, so one simple way is that the user sends the signature on chain and we verify it on chain entirely. That's what we call the on-chain verification mode. But there's another optimistic verification mode that we can do, and we call it the naysayer verification mode. This is just a toy example. So let's imagine that this post-quantum signature verification scheme consists of verifying the correctness of this multiplication. And you have food coma, you are lazy, you are a smart contract, you don't want to do any computation because it's costly. So you don't want to verify the correctness of this multiplication. So the left number is today, like 2025, June 30, and the right date is the birthday of John von Neumann. So who says this multiplication is correct? Hands up. Okay, who says it's incorrect, and why is it incorrect? Okay. Yes, please. Sorry? Yes, exactly. So, right, so computing, so there was a really great insight here. Computing this whole multiplication is toilsome and boring, and we don't want to do that. But there was a naysayer back in the audience who could give us a constant, succinct proof that this computation is incorrect. And the same logic applies to post-quantum secure signatures. Maybe verifying them would be really costly, but there might be some clever naysayers who says that, hey, look out, watch out, even though there's a signature on chain, I can prove it to you very succinctly that the signature itself is incorrect. And this is exactly what happened. Thanks, naysayer. So the user sends on chain because we don't want to send the entire post-quantum secure signature scheme, we just send a commitment to him, commitment to the signature. And there's a data availability layer, which can be call data, blob data, whatever. And the entire signature scheme can be visible at this data availability layer. You can implement it how you want. And there's a nice party, just like the gentleman at the back, who can observe this, reads this signature, and acts if and only if there's some nasty thing going on, meaning that the signature is invalid. And then can send a short naysayer proof saying that, hey, watch out, the signature is incorrect. And what's the point? The point is that if the signature is incorrect, nobody does anything. We just accept the signature as it is. And so that happens presumably 99% of the time. But if the signature is incorrect, then we just need to verify this short proof, which is much smaller and faster to verify than verifying the entire signature. And I will show you some examples. Okay, so this is what we did in our work. We took 4 post-quantum secure signature schemes and evaluated them both with full on-chain verification and naysayer verification. Okay, so the first one is VOTS Plus. It's, how many of you know Lamport signatures? Okay, so if you know Lamport, VOTS Plus is just a generalization of Lamport. If you don't know Lamport, then bear with me. So VOTS Plus is important because it's a building block of many other standardized signature schemes, such as XMSS and Sphinx Plus. And it's a hash-based one-time signature scheme, so that's the downside, that for one public key, we can only sign once. If we it's like basically XOR encryption. If you encrypt a message with XOR, then you are cooked. The same stuff here. You can only encrypt with a given public key only once. Okay, so VOTS Plus, for very simplified, but that's the gist of the signature scheme. Let's say we want to sign 3-bit messages. Then we have 8 secret keys, some random strings. The public key is the hash chain of these secret keys. So we apply 7 times the hash function iteratively. And if we want to sign a message, basically what we do when we sign messages, it depends on the message, how we sign it. So for instance, for message 1, we just need to hash the secret key 1. If the message is 0, then we just release the secret key. And now it's kind of intuitive how we can create a verification algorithm for this. So the verification algorithm, so for different messages, we have different length of hash chains. And the verification is basically you just need to finish the hash chain up to the public keys. That's the verification. So basically, if you didn't understand anything, the point is that verification is just a bunch of hashes, like brainlessly. And it's okay because in Solidity we have precompiles for various hash functions. But if we have a message, like the message is 0, 1, 2, up to 7, then this is the verification algorithm, what it needs to do. But if I tell you that that a naysayer comes along, just like the gentleman did 5 minutes ago, then the naysayer can point to the hash chain which is faulty, right? So if I want to be sure that the signature is correct, then I need to compute every single hash chain. But if the signature is incorrect and somebody helps me off chain, then I can much faster figure out, like, I just need to compute one hash chain, let's say this one. Okay, so this is on-chain verification costs for VOTS Plus. So it's pretty fast. So one signature for winter needs parameter 4 and 16 costs roughly 200,000 gas, which is not great, not terrible. But for winter needs parameter 256 is even worse. So this is on-chain verification, and what you can see is that the x-axis, I don't know if you can see it, the x-axis is the Hamming weight of the message. So as the Hamming weight of the message increases, we need to do less and less hash computation, so also the gas cost decreases. Okay, and these are the numbers for if we compare on-chain and naysayer verification. And no surprise, naysayer verification is much faster typically than redoing all the verifying the entire signature scheme. So how does the naysayer prover look like? The signer just computes a Merkle tree of the signature, and on-chain stores the Merkle tree of the VOTS Plus signature. And whenever a naysayer comes along, the naysayer needs to point to a part where the VOTS Plus signature fails. And what does the naysayer proof must contain? It must contain a Merkle authentication path, and also the contract needs to check that the opened positions indeed encode a faulty hash chain operation. So that's what the naysayer prover and verifier do. And these are the corresponding gas costs. So no surprise, the bottom line is that naysayer verification mode is faster on chain than verifying the entire signature. Another signature scheme that we benchmarked is XMSS. So these are already, if you want to verify on chain XMSS or VOTS Plus signatures, you can use our open source library. So VOTS Plus XMSS is also standardized not by NIST but by IATF at RFC A391. The downside of XMSS is that the number of possible messages that can be signed is upper bounded. So the idea is that the secret key is votes plus secret keys. The public keys are the public key of the scheme is that we compute the votes plus public keys, that those are going to be the leaves of the tree, and the root hash of this tree is going to be the XMSS public key. So, and now you can see why the number of messages that can be signed is upper bounded. So how does signing work in case of XMSS? The signature is a votes plus signature and a Merkle authentication path that corresponds to that votes plus public key. And the verifier needs to check the votes plus signature and the Merkle authentication path, and the verifier needs to increase the counter. Oh, I forgot to say that this XMSS is a stateful signature scheme. So both the prover and the signer and the verifier needs to have a state, but it's fine in the blockchain setting because storing a counter on chain is fine. So stateful signatures is actually a good fit for blockchain. Okay, how to naysay an XMSS signature? Either there might be two faults in a votes plus signature in an XMSS verification. Either the votes plus signature fails or the Merkle authentication path is faulty. So we've already seen together how we can do the votes plus part, but it's not clear how to naysay Merkle authentication paths. How many of you have seen Merkle authentication paths or Merkle membership proofs? Okay, so everybody knows. So if we want to prove that this value 2 was oops, no. Okay, so if value 2 is committed in this Merkle tree, then we need to release the black nodes. And so the black nodes are the Merkle path, but to be able to naysay a Merkle authentication path, we also need the gray nodes, the copath. So essentially we need the full verification trace in order to be able to check for somebody to prove the incorrectness of this authentication path. So a naysayer proof for a Merkle authentication path is double the size as the regular authentication path. Okay, so the naysayer proof is both the gray and the black nodes. And these are the numbers for XMSS. So what you can see is that the x-axis is, again, the Hamming weight of the message, and the y-axis is the gas cost. I don't think you see it, but basically kind of 4 million gas to verify an XMSS signature. And what's visible on this graph is that the Merkle tree height of the tree doesn't really affect the verification gas cost. Okay, so these are the numbers. So these are the on-chain gas costs, and h is the height of the tree. So if h is 20, then it means that we can sign 2 to the 20, so a million messages, and it doesn't really affect. So even if we can just sign 2 to the 4 messages, 16, that's also 4.3 million gas. But if we want to allow the signer to be able to sign a million message, that's still less than 5 million gas. And the naysayer for XMSS is a little bit more complicated because now there are 3 possible faults. But the bottom line again is that the naysayer verification mode is much faster than verifying the entire signature on chain. Okay, we also benchmarked one more, Sphinx Plus. I need to speed up a bit, which is standardized, as Antonio said 2 years ago, 2023. So it's a hash-based stateless signature scheme. There's a verifier. We built a verifier for that, so you can already verify NIST standardized signatures on Ethereum. And the last one that we benchmarked is Mayo, which is not a hash-based signature, but a multivariate equation system-based signature scheme. And now it's currently being standardized by NIST. It's in the competition, so hopefully they are going to win. It's a nice signature scheme. And it has small signatures, but largish public keys, which is not that great. And currently, sadly, this has pretty high gas costs, as you will see. But if we would have SIMD, which is kind of on on the roadmap. SIMD would also help for lattice-based signatures. SIMD allows you to do, because Mayo and lattices needs finite fields that are much larger, much smaller than regular elliptic curve finite fields. So for instance, Mayo needs 4 bits or 5-bit large finite fields, and SIMD would help, which is hopefully an upcoming upgrade, would help us decreasing the verification gas cost also for Mayo. Okay, so these are the number that you've already seen. This is the TLDR of this whole work. So are we happy? Not really, because these are like, who wants to pay transaction fees? Like anytime you send a post-quantum secure signature scheme, like, I don't know, $10 or $50, nobody, right? So if you buy a slice of pizza or croissant, then you definitely don't want to pay every single time $50. So yeah, as Antonio already said, on-chain verifications is pretty costly. Maybe we would need precompiles or some other way around. Okay, so again, here's the GitHub link, the paper link. I think it would be nice if these libraries would be formally verified. So just to make sure that what we built is meaningful and doesn't contain bugs. It would be even more amazing if people would use it, maybe not on L1, but on some layer 2s. Gas golfing these contracts. So if you're really into gas golfing, let me know. We didn't really spend a tremendous amount of effort to gas golf it and optimize it, but I think it's definitely possible. Yeah, would be nice to have some precompiles also for hash-based standardized signatures, not just Falcon, as other people are suggesting to do it. Okay, and yeah, there's many more open questions how Ethereum should transition to post-quantum. So I think this whole line of research and work has just started. And yeah, feel free to reach out if you want to talk about anything related to post-quantum or Ethereum in general. And yeah, there are many great ETH research posts, so I highly recommend you to look at those. And thank you. Let me know if there's any question.